Now let's begin by introducing the basic concept of a fusion reactor. This is intended to give you an insight into the working principles and the main parameters of a reactor. This is a picture of the ITER reactor. It will be the first ever reactor that intends to demonstrate that the output power generated by the nuclear fusion is at least 10 times the input power. That input power is needed to reach the conditions that allows enough fusion reactions to take place. This reactor, ITER, has a torus-shaped vacuum vessel surrounded by magnetic field coils. Inside the torus, the fuel gas is heated to about 150 million degrees, the temperature needed to reach fusion. This hot gas, which we call a plasma, is coloured pink in this picture. To understand why the machine looks like this, some basic physics background is needed, which we will introduce in the next few slides. A few questions might pop up when looking at ITER. Why is the machine so big? Couldn't we make it smaller and cheaper? I already mentioned that we need a temperature of 150 million degrees. Why this high temperature? And can we even reach that? How do we keep a fuel of this temperature in place? Which fuel to use? Well, here I can already answer that we'll use deuterium and tritium. I'll explain in a moment why this is the easiest. However, this choice immediately has far-reaching consequences. Tritium handling and the neutron radiation resulting from the fusion process makes it a nuclear facility. That's why nuclear safety culture has a high priority. And finally, why don't we have a working reactor yet? What are the main remaining physics and technology challenges? Now, let's start to discuss some fusion basics to be able to find the answers to these questions. Don't worry if you don't follow all the technical detail in the next few slides, because at the end, I'll summarize the main points that we need to remember. The starting point in our discussion will be to find out which fuel to use. For this, we first ask the question, what is the condition for fusion to work? Obviously, we need to get net energy out of the reactor. The energy set free in a fusion process originates from the release of the binding energy of the nuclei. Inside the nucleus, the strong nuclear force keeps the particles together, meaning it costs energy to break up the nucleus into individual particles. And vice versa, energy is released by bringing these particles together, the binding energy. The picture shown here shows how this binding energy varies according to the mass of the nucleus. It's clear that for light elements, this binding energy increases, whereas for heavy elements, it decreases. This is where nuclear fission is different from nuclear fusion. In fission, energy is obtained by breaking up heavy elements like uranium into smaller ones. But with fusion, we gain energy by combining light elements into heavier ones. As an example, this picture allows us to calculate the energy released from the fusion reaction between the two hydrogen isotopes, deuterium and tritium, leading to the production of helium and a neutron. In the formula, deuterium is denoted by 2H and tritium by 3H, because they are the isotopes 2 and 3 of hydrogen. When we talk about energy in atoms and their nuclei, we use a unit of energy called MeV. It stands for 1,000,000 electron volts. Now, the binding energy of a helium nucleus, with its 2 protons and 2 neutrons, is 29 MeV. And that's 17.6 MeV higher than deuterium and tritium together. So we've gained some energy, and this is the energy released. This energy is typically 10 million times more than the energy in a chemical reaction. So to get the same amount of energy, we need about 10 million times less fuel. By the way, the energy released can also be calculated using Einstein's famous equation E equals mc squared, which says that the change in energy is just proportional to the change in mass between the fuel and the reaction products. So the requirement for a working fusion reactor is that the power produced should be bigger than the power needed to reach the condition for fusion, to heat the fuel. The power produced is equal to the number of fusion reactions per second multiplied by the energy per reaction, which we have just calculated. The next step is to find out how many fusion reactions per second we can make. The number of fusion reactions of the two species of nuclei is proportional to the number of particles of both species, which we call N1 and N2. The relative velocity between the particles V and the so-called reaction cross-section, represented by the Greek signal sigma. This is a measure of the probability that fusion can take place. The probability depends on the kinetic energy, or the temperature, of the particles. In the figure, this fusion cross-section is shown for several different processes. From this figure, it's obvious that the probability of fusion reactions between deuterium, labelled D in the figure, and tritium, T, is at least an order of magnitude larger than for any other fusion reaction. So we can conclude that the fusion reaction between deuterium and tritium is the easiest. It has the highest probability and peaks at the lowest energy, so needs the lowest temperature. The products of deuterium and tritium fusion are helium and the neutron. The consequence of this reaction is that we have to deal with nuclear safety because of the tritium handling and the neutron radiation. It was clear in the previous picture of the cross-section that no fusion will happen if the kinetic energy for fusion particles is too low. The reason for this is that the nuclei are electrically positively charged and repel each other. Only when they come very close, a distance of around 10 to the minus 15 meters, the nuclear force dominates and the particles will fuse. Now, we can calculate what energy is needed to overcome this electrical charge repulsion, which is due to the Coulomb force. It turns out that it's best to do this at a temperature of 150 million degrees, since then sufficient particles have enough kinetic energy to overcome this Coulomb barrier. Now that we know which optimal temperature is needed, we can try to estimate how much heating power we need to reach this. Here, we have to realize two issues. Firstly, the heating power depends on the insulation of the system. How well is the energy we put in confined and not lost from the system? This is quantified by defining the energy confinement time, for which we use the Greek symbol tau E, the ratio of the thermal energy of the plasma to the power lost from the system. In the steady state situation, this power loss is equal to the heating power applied to the plasma. The larger this confinement time, the better we confine the energy, and the less heating power is needed. The second issue is that for a working reactor, this applied heating power has to be less than the fusion power produced. For ITER, the goal is that the fusion power is 10 times larger than the heating power. Now let's summarize where we are. We found that it's easiest to use the deuterium-tritium fusion reaction, since this has the largest reaction rate at the lowest temperature. We need a fuel temperature of 150 million degrees, since that is the optimized condition for fusion energy production and to minimize the energy needed to heat the plasma. several questions are still on our list. The most crucial one at this stage is to find a way to confine this hot plasma, to make sure that the particles and energy will not be able to get lost from our system. For this, a magnetic field has to be applied. A plasma at 150 million degrees consists only of charged particles, the bare nuclei of deuterium, tritium, and the reaction product helium, and the free electrons. If charged particles move in a magnetic field, a force acts on the particles, called the Lorentz force, proportional to the charge q of the particle, the velocity v perpendicular to the magnetic field direction, and the strength of the magnetic field B. The direction of this force is oriented such that it results in circular orbits of the particles around the magnetic field direction. If now the magnetic field is made into a torus shape by the grey coils in this picture, then in principle the charged particles will be confined in the reactor, circling around the magnetic field. This principle of magnetic confinement is the crucial ingredient for the reactor of the type of ITER, called a tokamak reactor. The energy confinement time, which we saw 2 slides ago, is increased by many orders of magnitude by applying this magnetic field. And the stronger the magnetic field, the better the confinement. That's why for ITER, we've chosen to have the strongest magnetic fields possible, which are created by superconducting coils and can be as high as 15 Teslas at the inside of the machine. Apart from the superconducting magnetic fields to generate the torus-shaped fields, the coils coloured grey in this picture, several other magnetic field systems are needed to keep the plasma in a stable configuration, like the blue coils depicted here. They have several functions, mainly to shape the plasma and to drive an electric current in the plasma. But basically, it all comes down to designing the magnetic field structure to optimize the confinement of the plasma and keep it stable. All these coils are made from superconducting material, since this leads to the lowest power losses inside the coils. It allows for continuous operation, and it can reach the high magnetic fields needed. And the strength of the magnetic field is important for 2 reasons. Firstly, since the magnetic pressure balances the plasma pressure, the higher the magnetic field, the higher the pressure of the plasma can be. The plasma pressure is related to the temperature and to the density, and so the total number of particles in the reactor. Secondly, as we saw earlier, the larger the magnetic field, the better is the confinement, represented by the energy confinement time, tau E. With the information we now have, we can begin to understand why ITER and future fusion reactors are so big. The fusion power produced depends on the volume of the reactor. A larger volume at the same temperature and density simply means that there are more particles that will fuse, so more output power. But the power needed to heat the fuel also increases if the machine becomes bigger. However, this applied power is to compensate for the energy lost from the system, and this power is lost over the outer area. Since the ratio of volume to area scales with the size of the machine, the bigger the better. That's why the presently operating tokamak jet is just not big enough to reach a net power output. ITER will be the first reactor that is big enough for this milestone. You may wonder how the heating of the fuel to the required 150 million degrees is done. Well, there are 2 main methods for this. The first is by the injection of neutral deuterium or tritium particles at high energy. These particles have been accelerated to very large kinetic energy, around 1 MeV, which is a much larger energy than the plasma particles. these particles need to be electrically neutral before they enter the reactor so that they are not deflected by the magnetic fields. Once inside the reactor, they will collide with the other fuel particles and in this way transfer their energy to the plasma. In ITER, we can deliver 33 megawatts of power to the plasma in this manner. The second heating method is by the injection of electromagnetic waves into the reactor, rather like a microwave oven. As we saw before, charged particles will circle around the magnetic field lines. Ions do this at a typical frequency of 50 megahertz, and electrons do it at about 170 gigahertz. It depends only on the strength of the magnetic field. By injecting radio or microwaves with the same frequency, the charged particles will be accelerated through a resonance. They'll gain more energy and so increase the temperature of the plasma fuel. The energy produced in the fusion reaction is released in the form of kinetic energy of the two products. 80% of the energy is in the neutron and 20% in the helium nucleus. Since the neutron is not electrically charged, it is not influenced by the magnetic field. It will not be confined in the reactor, but will end up in the reactor wall, which we'll refer to as the blanket. This blanket is thick enough to stop the neutrons escaping, and in the process, their kinetic energy is converted into heat. By removing this heat with cooling water and heat exchangers, the heat could be used to generate electricity using conventional generator turbines. That will be done in future fusion power plants, but in ITER, this final step of generating electricity will not be done. The other fraction of the fusion power, the 20% in the helium particles, follows a different route. First, since the helium nuclei are charged, they are confined in the plasma. The kinetic energy of the helium nuclei will be transferred to the plasma fuel by collisions with the plasma particles. In fact, this helps to keep the plasma at the required temperature. However, in the end, this power will also be lost from the plasma by a diffusion process. Now, the magnetic field structure is made so that the power lost from the plasma ends up at the bottom in a structure called the diverter. This is depicted by the yellow arrows in the picture shown here, which is a cross-section of the inside of the ITER reactor. The power load at the diverter, introduced in the previous slide, poses one of the major challenges to a fusion reactor. During normal operation, this load will be around 10 megawatts per square metre. This amount is already very close to, or even beyond, the maximum load that known materials can withstand. However, under certain conditions in a fusion reactor, the situation will be much worse. Regularly occurring instabilities in the plasma will increase this power load for a short time by a factor of about 100, yielding power loads close to 1 gigawatt per square metre. Now, the challenge is how to cope with this extreme interaction between the hot plasma and the material of the diverter. This diverter material, in ITER it's tungsten, will be exposed to large erosion rates, but must not melt under the intense power load, and evaporation must be minimized to avoid tungsten getting into the plasma and diluting it. Well, a final solution to this problem is not yet available, but the ITER experiment hopes to demonstrate that the diverter can survive reactor operation for several years. Most fusion physicists regard this as the biggest challenge in present fusion research. To finish this basic introduction, let's consider tritium. One part of the fuel, deuterium, is in almost unlimited abundance on Earth. There's 33 milligrams in every litre of ordinary water. But the other fuel ingredient, tritium, is almost absent. The solution to this shortage of tritium is that a fusion reactor should generate its own tritium. This can be done if the blanket contains a quantity of lithium, since the reaction between the neutron from the fusion process, which ends up in the blanket anyhow, and the lithium in the blanket will make a tritium nucleus, as well as some more helium. So the overall fusion reaction is actually deuterium plus lithium, resulting in 2 helium-4 nuclei. So far, that's the theory. Perhaps it's obvious that this fuel cycle requires a very high efficiency, close to 100%. This still has to be proven or demonstrated in ITER. This introduction has now given you the basic answers to be able to understand why the ITER reactor looks as it does, why there is the need for tritium, the high temperatures, the magnetic fields, and so on. To link this knowledge to the aim of the course, about the nuclear aspects and the radiation, the following things are worth remembering. The fuel consists of deuterium and tritium. However, in a power plant, the tritium will mainly be bred inside the reactor. The fusion reaction produces a large number of highly energetic neutrons, which will have several consequences. A thick blanket is required to stop the neutrons, structural properties of materials will be changed, and radioactivity is induced in the materials upon bombardment by neutrons. These nuclear aspects have a substantial impact on the safety culture and work procedures, as we will discuss next. Before we proceed, you may like to answer some short questions to check your understanding of what we have learnt. Thank you for your attention.